Hello, everybody. This is great. How many people are here? We are going to get started, so if you kind of settle down, we have a great opportunity here today to learn about quantum everything with a panel who will all introduce themselves. My name is Zach Setlin. I'm the Dean of the STEM Division here at Foothill and also lead the program Emerging Technologies Institute along with Constantine here, for which this is under the umbrella of this event here today. And help yourself to snacks, waters, there's coffee if you haven't had some already. I'm here as a observer. I'm not going to be part of the conversation, but I believe that this is supposed to be a dialogue, yes?
Yes, it's very interactive. So ask your questions, interrupt, distract, and we get stuck with slide number 2. So it's okay. It's about it's exploratory. That's what we do in ETI. So Zach and I, he's my boss, my dean, but we are also working together as coordinators for emerging technologies. We're a team. And thank you, Michelle, for coming as well.
Yeah, so thank you all. I'm going to let them all take over and let's enjoy the talk.
So I'm gonna go over very briefly. It's gonna be quick at times because this is exploratory. We just want to make sure that everybody is into AI and stuff like that. But this is the tsunami that's coming, quantum technology, science and technology. This is a big event, big news. That's gonna change how the human species looks at the world. So we're gonna do some introductions basically here. Then ETI, very quick intro, Dr. Bill. Dr. Bill is the white-haired guy here. He's brilliant. They're all brilliant. And Nati, actually, no, that's Christian. Christian is next. He's down here. Then Dr. Zerger, you know him. So he's your instructor for most of you. And then we have Christian.
And I'm the least qualified.
And Nathaniel is basically here because he has a cat whose name is Schrodinger. So, and he's going to talk about that next. Okay, so this is basically who the presenters are. Next. And I'm gonna go quickly because this is exploratory. Each one of these can take 2 hours. But if there is interest in the physics classes and in the instructors like Dr. Caleb, we're gonna do more of these workshops. Next. Okay, so so this is part of the Emerging Technologies Institute that was created a couple of years ago. It's under Zach, our standing and dean, but it's cross-functional across the whole campus. And it's 9 technologies, 10 labs that we're building. Next. So we have a virtual reality lab. In fact, there is a group of students in there now. Next. And we have the AI learning community that Zach, yeah, he runs the AI learning community. And so that's the AI. And basically all of this stuff, I'm just introducing it to you. But you can just, if you have any questions at all, just write to eti@fhda.edu. And that's shown up there as well. And I'll write it on the board also. So next. So we have a special class for students that will work with certain challenges. And so we basically teach them how to build robotics. This is all part of with the DRC Disability Resource Center. So ETI gets involved in a lot of consulting, a lot of presentations and exhibits and so on. Next. We also help a lot of students with their projects, and they also get to publish in this magazine. How many have seen Principia? Raise your hand. Awesome. So all of you should be raising your hands soon. You can be published here. So when you apply for a job or for your application to transfer and so on, publications always differentiate your resume. Projects and publications. I know because that's what I used to do before. I worked in high tech. And I had 4 schools, San Jose State, UC Davis, Stanford, Berkeley. So this is what I would look for. I would look for publications and projects. So it's good for you guys to publish your projects. Next. Okay, so it's interdisciplinary, collaborative, and so on. And all the clubs, we have about 26 clubs last quarter, and we're still counting this quarter. Next. And this is basically the workshops that Zach, myself, and Carl. What is Carl? Oh, and this whole ETI team puts together. Next, let's see. So the virtual reality. Why is it important? these are new tools to be added to your toolbox, to learn how to use them. So next. And we provide forums, Zach and I have presented already, we go to various conferences and so on, and we present what we're doing here. The state of California definitely is interested in what we're doing. Next. So this is the address I mentioned, eti.fhda.edu, and then you can also see the website, google.edu/ETI. Also, there are cards in front of you, ETI cards and stickers. And so those also have the address. So if you have any projects in mind or anything else, contact us. And we also, at some point, I guess we have office hours, but now you're teaching as well. So we'll see what we do. Come on in, guys.
Yeah,
Next.
there's one chair right there.
Okay, so that was just the introduction, basically, because it's part of the Emerging Technologies Institute. So now we're gonna start the real show with Dr. Joe Zaglia, who is he changed this. Yeah. Oh, we're gonna, yeah, hold on.
My own set of slides.
You want
And
his own
4x3 format.
Okay.
First slide. First slide. Slide all the way up. Click on.
Oh, I'm gonna go.
Click on that slide.
Okay.
Hit the play button.
Play button here.
Okay, there we go. All right, so if you didn't know, this is the International Year of Quantum Mechanics. Why is it this year and not some other year? Anybody?
I'm just gonna make it educated guess. Did something happen in 1925?
Okay, yeah, something happened in 1925. Actually, it's kind of like 24 through 27. So that's the period I'm pretty much going to cover. I'm pretty much going to do a history about, why we're saying this is the International Year. Now, this comes from the United Nations, and every year they pick something. So back in 2005, it was the International Year of Relativity because 1905, Einstein did his relativity. And then the next year, it was the International Year of the Potato. So, I mean, it's not all about science. Okay. So, I'm actually going to jump back to Einstein, not because that's actually the first beginning of the story, but he did some things that tie into what happened in 24 and 25. So if you would go to the next slide, please. Okay, so here we have Einstein. And of course, as you can see, because we are Zoom, our titles are missing. So that's a real problem with slides. One thing is never go all the way out to the edges of slides, because by the time you project it, something gets cut off. So this is 1905. He came up with special relativity, which everybody assumes that's what he got his Nobel Prize for, but no, he didn't. He actually got it for the beginning of quantum mechanics, where he proposed that light, something that we had thought by this point was a wave of electromagnetism from the 1800s, found out that in certain aspects, it seemed to behave as if it came in little tiny packets. And he's the one that really came up with that idea and called them the photon, that actually the photon was the smallest indivisible part of light. So if I shine some red light at you, it's coming in photons. You can have 5 photons, 4, 1, but you can't have half a photon. Your eye is so sensitive, it can respond to a single photon. Usually it takes 2 or 3 for you really to realize you've seen it. The main factor is that the energy of a photon is related to its oscillation frequency, and the coefficient of proportionality here is Planck's constant, which, so Planck did something in 1900, which you'll hear about in physics class when you get that far. But it's a very small number. Everything to deal with quantum mechanics has got Planck's constant. Next, please. 1913, Niels Bohr comes up with a model of the atom to explain this. So, oh, that's interesting. How did that get cut off? Okay, interesting. There should be 2 more lines here. When you look at the spectra of hydrogen, so you look at it in a prism, you see a bright red line, a bluish line, and then 2 violet lines. As opposed to when you look at a hot coal in the fireplace, you see a rainbow of colors. And when you look at the sun, it's a rainbow of colors. So this was really confusing. Bohr comes up with a theory that works, that the idea that the electrons orbit the nucleus, but it's discrete. Again, the word we're going to keep using over and over again is quantized, that it comes in little packets. You can have 1, 2, or 3. You can't have 1.5. Why? Well, that's the mystery. All right. And electrons can jump between orbits. So if it's in a higher orbit, it can jump down and emit, for example, a red photon. And conversely, it can absorb exactly that color and jump up. But only certain orbitals, there's more up here. And in chemistry class, you learn about the 1s orbital, the 2s orbital, the 3s. This would be like 1s and 2s orbitals. Next, please. Compton, so now we're getting close to our time, 1923, showed that he could actually collide a single photon with an electron. It was like playing pool. So in mechanics class, you learn about when you have collisions, you conserve what?
Energy.
Energy, yes. Okay, energy was conserved as if the photon had energy. Well, what else do you conserve?
Momentum.
Momentum, yes. And that was the key, is you discovered through this that the photon also had momentum, just like a particle. And the momentum was given by Planck's constant divided by the length of the wave. So now we've established that frequency is basically proportional to energy and momentum is proportional to wavelength. Next, please. You notice that almost all these guys got a little notation down here of the Nobel Prize. It's interesting to note sometimes that it's within a year or two of their discovery, and sometimes it's like 20 years later. There was just too many of them to give the Nobel Prize to them. So it's like, okay, who's next? So, whoa, no, De Broglie, we want De Broglie here. So this is 1924. De Broglie makes the big leap that, we thought of light as being a wave, but then we began to realize that no, it's sort of acting like a particle. I wonder if things that we think are particles, like electrons, actually have wave-like properties. We have more people who are trying to get in. Please, come on in. Constantine, find some chairs for these people.
Gonna find some chairs.
Yeah, okay, so this was a big jump. Now, this was his PhD thesis. And really, the entire thesis doesn't have really complicated mathematics. It's more algebraic and ideas. And the guys looked at this and went, is this really a PhD thesis? And they sent it to Einstein. And Einstein looked at it and said, this guy's a genius, give it to him. And so De Broglie gets the Nobel Prize for his PhD thesis. That usually doesn't happen. Nobody has certainly given me any sort of prize for my PhD thesis. Caleb, how about you? No? Okay. So, yes, doesn't happen very often. So he uses the same idea that the energy of a particle, which you think of like an electron, is related to the frequency, and the momentum is related to its wavelength. What's the proof? Well, you start looking and see, can electrons behave like waves? And one of the main things that waves do is cause interference. So if you have two waves and they're arrive out of phase, they cancel. That's how noise cancellation earphones work. So this is a case, I know it doesn't really say much, but it's electrons going through a crystal. And when it came through, you had diffraction. That's another property of light. So that pretty much nailed down that, yes, this is true. And the guys that did this 1927 experiment, they got Nobel Prizes too, but I didn't include their names. All right, now, but, a wave goes on forever. So I'm used to thinking of an electron as something that's like here, or maybe it's here. De Broglie showed that if you combine different frequencies together, you can make a wave packet. So you might consider that this is the electron traveling with this sort of like internal wave-like structure of, I'm not sure what, and it's traveling. And you notice that because it's a blob, it means that the electron has, it's somewhere in here. I'm not sure exactly where it is in here. And as a matter of fact, that is a little uncertain. Let's go on. Okay, I'll mention this just to be complete. Heisenberg presented the first form of quantum mechanics in its modern form, 1925. Oh, here we are, 1925. We've arrived. His method involved matrices. Okay, how many people have played with matrices? Let me see hands. Okay, so you know what they are. Usually learn them in linear algebra or something. It's very abstract. We generally don't start you with matrices in undergraduate classes. We kind of avoid them as long as possible. As a matter of fact, up to this point, most physicists avoided matrices as well. They required a mathematician, Jordan, to actually, Jordan and Bourne, worked with him to actually bring up this idea. But mathematically, we find that things that should commute, momentum and position, if I put them in the reverse order, now you're used to 3 times 2 is 2 times 3. Well, it turns out that in the quantum world, that's no longer true. And they differ by a small amount, which guess what, is proportional to Planck's constant. For some reason, the H bar disappeared there. And again, look, an imaginary number shows up. So you seem to always have Planck's constant, and somewhere close by, it's probably an imaginary number. It seems you need imaginary numbers to do quantum mechanics. Why? Well, that's a good question. All right. Interestingly enough, he gets the Nobel Prize. Jordan does not, and neither does Bourne for this. Next, please. Back up 1 year. So going back to spectra, it was found that when you put a magnetic field across your spectral tubes, when you're looking at the spectral lines, they would split into multiples. Now, some of this was explained by a single line going into 3 because the p orbitals, you have 3 p orbitals. And one will be aligned with a magnetic field, one will be anti-aligned or something like that. So that was the original explanation, which worked okay. But then they found that some lines split into 2, and that didn't fit this idea. It was proposed by Pauli that there was a new quantum number, which evolved into the concept that the electron is a little ball that's spinning. It actually has an angular momentum associated with it. And because if you have a charge and you run it around in a circle, that's like a current, you make a magnetic field. So that the electron itself is also a little magnet. And then it either aligns or anti-aligns with the magnetic field. And if it's lined up, the energy will be slightly lower if it's this way. So as the electron jumps from a high orbital to a low one, its spin could flip over or it could not flip over. And that gives you 2 slightly different lines. Pauli came up with the description of this, and it introduces a concept that there's more than scalars and vectors. So scalar is like mass, number 3, temperature. A vector is which way did he go? And I go that way. That's a vector. It's got an arrow. And a vector, if I rotate by 360 degrees, I end up right back where I started. A spinner, which seems to describe an electron, is a different animal. It was called the mysterious tribe. And it's one of those things that when you rotate by 360 degrees, this is going to fall out of my hand. You're not back to where you started. You have to rotate again. I'm sorry, I just can't do it. Okay.
But I rotated by 360 degrees, and now my phone is like upside down, right? Whereas I rotate it like that, and now it's in a different position, so I have to rotate it again to come back to where I started.
Thank you.
It's kind of funky.
I need him for that. Yes, sir.
Is it kind of like quaternions, or is that a different thing?
Oh, that's very good. Come in and talk to me. I'm here all day on Wednesdays. I'll talk to him about quaternions. I'll talk to him about quaternions. Okay, so yes, quaternions are a way of representing this. So what you have is an object that you must rotate 720 degrees to get back to where you started. So it's not a vector, it's not a scalar, it's sort of halfway between a scalar and a vector. That's an electron spin. All right. And in doing that, he introduced another form of matrices. Next, please. All right. Now let's take nitrogen. Why don't all the electrons drop down into the lower orbit? It's forbidden. If they could, then every single atom, everything would be in the 1s orbit, and all that interesting chemistry would go away. Turns out that you can only fit 2 into that first orbit. You could fit 8 into the next one. Why? Yeah, okay. Pauli proposes the exclusion principle, that electrons, you can't put 2 electrons together in the same state. They could have opposite spins, that's fine, now they're in different states, but you can't be in the same state. Why? Well, that's really interesting. It is a basic feature of certain types of matter. About half the particles obey this. They're called fermions, after Enrico Fermi. The other half don't. That would be like photons. Photons you could stack one on top of the other. That's how you get lasers. You get every single photon is doing the same thing, going in the same direction, exactly in phase. But you can't do that quite with electrons. It's still a mystery. I mean, there's math that supports it, but it's still kind of a mystery. Let's move on. All right, this is 1926. Schrödinger comes up with an equation that de Broglie waves will be the solution to. And what you do is you replace momentum. So this equation would be p squared over 2m. That would be kinetic energy. But you rewrite the momentum as being a derivative of the wave function. And this would be the potential energy, say, inside the atom. And that's the energy. It's a differential equation. That's why you take differential equation. Am I getting close?
5 minutes.
Okay, well, I'm fine. So I'm 9 minutes. That'll take me to 14. Okay. So you've probably seen a picture sort of like this of all these weird orbitals, the SPDs, and they all look weird. You go, where did that come from? It comes from this. If you solve that equation in spherical coordinates, you get the orbitals, these shapes. But what exactly is a picture there? I mean, it's really a picture of this wave function thing that, particles are a wave. They haven't really told you what the wave really means. Now, at this point, they were mostly interested in calculating what the energy was. They didn't care really about, maybe the interpretation of what the wave function was. Next, please. Max Born came up with an interpretation that the square of the wave function is the probability of finding the electron in a certain place. So you got the p orbit that goes like 2 lobes like this. It means it's more likely to be here. It's hardly likely to be there at all. You may think of the wave function as the square root of the probability of finding it times some sort of complex factor which has the wave-like properties where you can get interference. Next, please. Heisenberg uncertainty principle. So Heisenberg recycled here. This is 1927, I think. And he shows that you cannot measure precisely the position and the momentum of something simultaneously. There is a minimum uncertainty that you get. If you really constrain it down to, I know the electron's right there, then you become totally uncertain of its momentum, which means a second later, you have no idea where that particle is. And you just, no matter what you do, you cannot exceed this limit. Next, please. All right, now sort of towards the tail end, this gets more in 27 and 28. Dirac came up with an equation that was relativistically correct. And it had 4 components. Okay, this math here, we generally don't teach this at an undergraduate level. You usually get it at a graduate, although if you want to explore it, I can teach it to undergraduates because it was taught to me when I was only a sophomore. If you use something called Clifford algebras. But the components are spin up, spin down, and the other two. And he said, I think this is an opposite particle and antiparticle. He invented antimatter theoretically before it had been seen. And it's a couple of years later before somebody actually finds the anti-electron. So Dirac is famous for really coming up with the idea of antimatter is a natural solution to the problem. You might notice this statement. You consider an anti-electron as an electron moving backwards in time. That's kind of a mind twister. Next, please. All right, all of these people and a few more ended up in the 1927 Solvay conference. I believe it was in Belgium in this case. And you see all sorts of people. You see Niels Bohr right there. You see Pauli right there. You see, what is this? Einstein. Yeah, well, Einstein, Madame Curie, Lorentz. And then this row is really, you see Niels Bohr, you see Born, de Broglie, Compton, Dirac.
Where's the lady?
Curie, Madame Curie. So, and at this conference, they pretty much got all the ideas together and came up with what they thought was what it all means. Next slide, please. So in a dual talk by Heisenberg and Max Born, they said, we consider quantum mechanics to be a closed theory whose fundamental physical and mathematical assumptions are no longer susceptible of any modification. So apparently in 1927, they thought that they had it all tied up. Now, this periodically happens in physics. People say that, you know, we're at the end of physics. That was done in 1900. When Michelson said, you know, all we're doing is measuring the next decimal point. There's nothing new to be discovered in physics. Go and be something useful. Become a lawyer. You know, do something useful. Because, you know, physics is over. It's done. And there's been a popular book that was out there a decade or two ago, The End of Physics. There's somebody always talking about the end of the world. Excuse me, the end of physics. But what happened after 1900? We got relativity and quantum mechanics. So we're not done. So next. So that's the question. Is this the end of the story? And I think you'll find out from these guys, they don't think that quantum mechanics is dead.
Thank you. Okay, so now we're gonna switch.
Okay.
Yes. While he's getting the slides, everybody clap for Dr. Bill. You already did. Not do it again. That was great. Dr. Bill talked a lot about fancy math, and I suspect that might have been a little bit overwhelming, especially for people who are not mathy people. So my goal is to express this in a way that will be a little bit more intuitive and a little bit, you know, like less mathy, okay? And I will flash one equation on the board and I will say, this looks horrible, don't worry about it. That is my promise to you. Okay, so Dr. Bill briefly talked about particles being kind of like waves and waves being kind of like particles. How do we know this? So this is a very famous experiment in physics in general. Especially in quantum mechanics. Why? Because, okay, let's talk about this experiment. It's called the double slit experiment. Imagine you have a barrier. You've got two slits in the barriers. You send a particle through the barriers. What happens when you send a particle through a slit? Right? It just like goes straight through. And that like is kind of intuitive, right? You throw a ball through a hole in the wall, it's going to end up on the other side of that hole. You throw a ball through a different hole in the wall, it's going to end up on that side of that hole. And so that's pretty intuitive with like classical particles. It kind of works fine. With waves, if you have like water or light waves or something going through a double split, the waves tend to interfere with each other. This is a property of waves. You'll learn this in like physics 4C, or if you took physics in high school, you might have learned this. But waves tend to interfere and they cause this pattern, which is more than just two, you know, clumps. It's what we call an interference pattern, right? So, you know, physicists say in like, you know, I don't know, 1927 or something like that, they said, well, you know, let's try shooting an electron through a very small double slit. And Dr. Bill talked about this. And guess what we see? Wow, holy shit. Like, you know, what the hell is going on here? Your electrons that are like, electrons are particles, right? But then at the same time, that looks like an interference pattern to me, right? So your electrons, there you go. Your electrons are behaving like waves. And so like what gives, right? Moreover, you can ask like, well, okay, the electron's behaving like a wave. Well, which slit did it really go through? You can put a detector in this slit, or you can block off one of the slits, and what do you know? It stops behaving like a wave. So as soon as you look at the electron, it's behaving like a particle. If you're not looking at it, it behaves like a wave. So you go, well, that's like really spooky, right? Does the electron know when I'm looking at it? Does it know like when I'm paying attention? And so it really seems as though, you know, the electrons behave like particles when we look at them, when we measure them, but they behave like waves when we don't look at them. Okay, you know, that's really fun. Okay, so then physicists go and like Dr. Bill said, oops, they say, well, let's try and define this wave-like property. And yeah, Dr. Bill did discuss this. That you have a wave function. It's denoted with this Greek letter psi. And this isn't math, this is just a letter. And it is this wave, right? It's called a wave function because it's wavy. Physicists tend to do this. We're not like chemists, we just call things what they are. It's wavy, we call it a wave function. And it has a real component, that's the red, and an imaginary component, that's the blue. And you say, wow, imaginary numbers, that's scary. But really it's like, you can think of it in this kind of 3D sense. And it has an amplitude. That's this black line, right? That's the amplitude over, you know, the distance. And then you ask me, well, okay, Nati, what is this wave function? And I go, dude, I don't know. Nobody knows. Nobody really knows what the wave function really is. What we do know is that the square of the amplitude of the wave function gives you a probability density. When I go back to this slide, if we send one electron through the slit at a time, it has a probability of appearing here, or here, or here, but it has a very low probability of appearing somewhere in the middle, right? So that's what the wave function really tells us. Really, it's just a probability density. Then you say, well, what happens next? And Dr. Hill talked about this. We have the Schrodinger equation. You say, wow, that's really horrible. You know, I don't want to think about this math. And I agree with you. I don't want to think about this math either. I'm just an undergrad. I don't want to think about it. But we can solve it. And you know, that's how it evolves over time. It kind of just, you know, does its thing. And that's great because now we know what the particle will do next. That's pretty useful. You don't just know what the particle is doing now. You can know what it does in some time. Then you look at this wave function, you say, well, wait a minute, hold on. The particle is kind of here, and it's kind of here, and it's kind of here. Like, it really seems to be like this spread out, you know, haze and not a definite position. And because the particle behaves like this wave, well, couldn't we say that the particle behaves as though it is both here and here? Ooh, that's like really funky, right? Because what if we split this wave function, right? Suppose we have this like, oh no, my little arrows are gone.
Yeah.
I had arrows that pointed to here and here. Just trust me on that one. So suppose we split the wave function in two so that it has an equal probability of being here and here. And what do you know? The particle behaves as though it's in kind of both places at once. It's a bit of a misnomer. It's a special kind of superposition, but that's really funky because now you can start dealing with, you know, things existing in more than one place. Like, when was the last time you felt like you were here and there at the same time? I don't know. I don't feel that way most of the time. But
Natty, before you leave this, you want to tell them that this is, you're running into a barrier?
yes, yeah. So in here we have an energy barrier. And there's some probability that the wave function will tunnel through, quantum tunneling, and some probability that will bounce back. We're not going to talk about how or why specifically that works. Just trust me on this one. I know I'm sounding like a chemistry professor right now. Okay, quick tangent. This is my cat. His name is Erwin Schrodinger. Here's his like, you know, ID card. I'm not bullshitting. That's actually his name. He's very cute. This is him sleeping on my piano. Why am I bringing up Erwin Schrodinger, my cat, not the physicist? Has anyone heard of Schrodinger's cat? Yeah, okay, that's a pretty famous thought experiment. Now, Schrodinger's cat, the cat has a chance of dying, but I like my cat, so I'm not going to kill him. Instead, this is Schrodinger sleeping on a speaker on my desk. Oh no, again. I had such a nice like drawing of a detector and like a table or whatever. Okay. If the particle ends up here, it sends a pulse to my speaker and it wakes up my cat. Okay.
Showed up there for a moment.
Yeah, I know the detector showed up for a moment. And it wakes up my cat. Okay. If the particle bounces back and it doesn't hit the detector, the speaker doesn't make a sound, my cat stays asleep, okay? But, again, if we're not looking at our particles, they behave like waves. So does that mean that if I'm not looking at my cat, and I leave the room, I go to the living room, and I, block my ears so I can't hear the speaker, does that mean that my cat is both asleep and awake at the same time? Does that mean that my cat is in a superposition of the particle going here and making a noise from the speaker and going back here and not triggering the detector and making a noise to wake up my cat? Well, that's a good question. We say that the cat is then entangled, okay, with the particle. And Mr. Zerger is going to quickly talk about entanglement, and I'll be right back.
Cool. Yeah. So to talk about what quantum entanglement is, I'm gonna go over to a simpler example than a whole cat. A whole cat's made up of a lot of particles. So we're going to talk about what happens to quantum entanglement with just a couple of particles first, and then yeah, Nati will bring this back. Okay, so okay, yeah. So first we can think about these slides. Yeah, there's one. Okay, there's a bunch of stuff missing here, but this is good. I can quiz you. So if I flipped a quarter, what is the probability that it's gonna land on heads?
49.9%.
All right, good. All right, let's pretend that it's a quarter that's designed to be 50-50. So it's 50% heads, 50% tails. If I take two quarters and I have one that's heads and one that's tails, I flip, then I close them in my hand so you can't tell which is which. I pull one out, I flip it, and it's heads. Then I pull the second one out and flip it again. What is the probability that the second one will be tails? 50%, right? Yeah, there's nothing going on here. These two quarters are not dependent on each other in any way. Every time I flip a quarter, I get a 50% chance that it'll be heads or tails. But as it turns out, when you consider things from a quantum mechanics perspective, things can get kind of weird. So what I have here unlabeled are these are supposed to be electrons, and electrons have this property that's mentioned by Dr. Phil called spin. Basically, what spin is, if electrons act as if they're spinning. If it's spinning, let's say counterclockwise, we call it spin up. If it's spinning clockwise, we call it spin down. If you've taken electricity and magnetism, this is because the magnetic field either points up or down for these electrons.
Right hand rule.
Yeah. Remember your right hand.
That's the difference again.
But yeah, so and normally when electron is just floating in free space, this electron, you can consider it to be in a superposition of the spin up and the spin down state. So just like we talked about a wave function in some sense being both here and there, and it's only when you measure it that you measure it in one place or the other. It's the same thing with an electron. So an electron is in a superposition of the up and down states. When you make the measurement, therefore you get a 50% chance of measuring spin up, a 50% chance of measuring spin down. So this, you'd think this is just like a quarter. But now we want to think about this experiment with the quarter where you take the two quarters that started out one heads and one tails and then flip them both, but with the case of electrons. So let's say we do something special. Oh, no, now it's both works. Okay, all right. So let's say we do something special here with these electrons. So in a superconductor, yeah, you may have heard of superconductors before, so you don't have to know what they are. But in superconductors, electrons are formed into these things called Cooper pairs. And Cooper pairs have a total spin of 0. So that means that if you try to think about the individual electrons in the Cooper pair, you can think about it as one is up and one is down, or one is down and one is up. But just like with other things in quantum mechanics, it's not really that one is down and one is up. It's that it's sort of in a superposition of these two possible states here. But no matter what, the total spin is 0. So this is kind of like I had the two quarters in my hand, a heads and a tails, and you don't know what they are, but you know one is heads and one is tails. Now, if we take these electrons that are combined in a Cooper pair, but we separate them, so they're not in this pair in the same sense anymore, but they're still what we call entangled. So this means that they're still a part of that same quantum state. In order to define their quantum state, well, you have to consider the wave function of the combined system of both electrons. And we know here that both of these electrons can be either spin up or spin down once we actually measure them. So remember, before we measure them, they're not spin up or spin down. It's only once we measure them. And so what is the probability going to be if we measure the first one? What's the probability going to be that we measure spin up?
Not a trick question.
Yeah, not if yes. Yeah, 50%. It can be either spin up or spin down. We measure, oh, okay, well. Okay, you're right. We measure 50% chance for the for spin up here. Is that really not? Okay, I said spin down. We measure 50% chance of spin down, but if we actually make this measurement and it is spin down, now someone else Now someone else is going to measure the second electron that is somewhere else. And what do you think the chance that we measure spin down is for this other electron?
0.
Yeah, exactly. Now,
Well, hold on, someone said 50%
Oh,
and someone
someone
said 0. We got a debate going on here.
okay. Yeah, where's the? So why do you say 0?
Who thinks it's 0%? Raise your hand. Okay, who thinks it's 50%? Okay, 50% Cam. Spin is analogous to angular momentum, right? So if one of them we measured spin down, is there then a 50% chance that we violate conservation of momentum?
Yeah.
Okay, we have a guess. How about the 0% chance? How come the second electron suddenly knows the spin of the first electron? We'll come back to that.
It's like a glove, right?
Let me make one other point. Some of you said 0, some of you said 50, and some of you said nothing. You guys are in the superposition state.
Yeah.
We're gonna measure them then.
You're also in some sense the most correct. So it's not
Yeah.
actually 0
Yeah.
or 50 in the real world. But yeah, what Navi said is right. If you're starting out in this combined state that has 0 angular momentum, so a combined spin of 0, and you're keeping this in the same entangled state, so this is still described by one quantum state. If one of them is spin down, for the total spin to be 0, the other one you have to be measuring spin up. And so this is a way that quantum mechanics is different than regular mechanics. This is different than just the case of of flipping your combined quarters. And so this is something interesting about quantum mechanics that that you can't get just classically. You might say, I don't know how impressive this is you separate 2 electrons by some small amount. And you can guess the spin of one from the spin of the other. But this is something that progressively scientists have been demonstrating over further and further distances. So for example, this experiment in China, they entangled photons, which we talked about before. You have one photon that has a polarization in one direction, one photon that has a polarization in the other, that are entangled. And what they found is that if someone measures the polarization of one of these photons, then they immediately know what someone 1,200 kilometers away is going to measure for the polarization of their photon. And again, this is what makes this unique for quantum mechanics is that it's not that one of them had a left polarization all along and the other one had a right polarization all along. It's that they both had existed in a superposition of both states until someone measured one over here. And then that means that someone 1,200 kilometers away is going to measure the other one over there. So, for those of you in 4A, we talked about how, forces only happen between either things like gravitational fields or things directly touching each other. But in this case, we have what appears to be some sort of interaction between 2 things that are separated by some great distance, where as soon as you measure one, you also collapse the state of the other one 1,200 kilometers away. And so this is a really weird thing about quantum mechanics that has some subtle nuances to it that I think Nazi's gonna jump in.
Okay.
But yeah, probably you want
How do you, so you said that you can entangle 2 electrons?
Yeah.
So how do you, aren't there like bajillions of electrons between any 2 electrons? So how does it not get interfered with some other electron and you get?
Yeah, so that's
Ask an experimentalist.
It's like trying to talk to a person in a big party, right? How do you?
No, so that's why I said that the people who said 0% were also wrong, because it's never actually 0% chance that you're going to measure something else, because other interactions with whatever environment it's in can cause the quantum state to decohere. So depending on the system to actually do these experiments, you have to really carefully design your experiment, which is why it's really impressive they managed to do it 1,200 kilometers away, because that's a lot of stuff that could interfere with your experiment. But yeah, I'll let him.
So really quickly before we run out of time. So Zuri mentioned that we can entangle these 2 electrons and we know that one of them has to be spin up and one of them has to be spin down. We don't know which one is which. until we check. So suppose for a moment that we give one electron to Alice and we give one electron to Bob and or Bill. And Alice moves all the way to one edge of the observable universe, and Bill moves all the way to the other edge of the observable universe. Okay, and Alice checks the electron, checks her electron. Okay, and what do you know? Alice's electron is spin down. By quantum mechanics, she knows instantly what the spin of Bob's electron is. Where's my right? Okay, we say, hold on. Einstein said nothing can travel faster than the speed of light. If these guys are like many light years away, shouldn't that mean that it would take years and years for Alice to know what the spin of Bob's electron is, or Bill's? Well, that's a problem. And Einstein really thought that was a problem. That's the E in EPR. It's the Einstein-Podolsky-Rosen paradox. And now, this was like a big paper and it caused a big stir in the science community. It was like 1930 something. Do you know something about that? I don't know, whatever. And it was unsolved for many years because Einstein called it spooky action at a distance. And you think that's a joke, but that's genuinely what he called it in the actual paper. Because that was really spooky. Having, one electron communicate with another over the course of potentially light years instantaneously. That violates the key tenet of relativity. One second. And so Einstein proposed, probably what if like the electrons knew all along, yeah, well, this one's always spin down, that one's always spin up. I'll give you an example. Suppose I have like two balls in a box, a red ball and a blue ball. Red ball and blue ball. See what I'm doing here? I put them in the box. I tell Alice to draw one ball and Bob to draw one ball without looking. And then Alice goes to one side of the universe. Bob goes to the other side of the universe. Alice looks at her ball. Okay, obviously Alice is going to see the blue ball. If she knows that the other ball is red, then that's instantaneous. Sure, that's not a problem. That's what we call a hidden variable. That is, Alice doesn't know the color of her ball until she checks it. Hence hidden. And hence variable, because it can be something else. The other option, which violates Einstein's theory of relativity, is non-locality. Okay, so hence arise, various theories of quantum mechanics that I know I'm trying to do that are hidden variable theories. And it was very okay. There you go. And until the 50s, it was really an unsolved problem until Bell Labs, you might have heard of it. John Bell made his famous Bell's theorem, which I'm not going to discuss the specifics of, but using various Bell tests, they were able to prove that locally real hidden variable theories, given the assumption of measurement independence, could not exist. That's a big problem for quantum mechanics because that makes it incompatible with general relativity, which is like the most successful theory of all time. And so the question becomes, well, is the universe not locally real? Okay, what are these assumptions? These assumptions are whether or not you decide to conduct the experiment, that's this one, doesn't change the outcome of the experiment. This is like key assumption of like philosophy of science. Whether or not you decide to make an experiment shouldn't change whether or not like the experiment happens or the outcome of the experiment too drastically, right? Next one is locality, i.e. things can't travel faster than the speed of light. You can't teleport. I can't go from here to like Yosemite instantly, right? It takes some time. And then the last one is realism. Realism is things exist when I'm not looking, which is, seems pretty obvious, but the idea is like, I close my eyes. I know that Bill is probably still over there. And I know that you guys are all still here when I close my eyes. That's what realism is saying. But Bell's theorem, and this was experimentally verified, I'm not going to tell you how because I'm not an experimentalist, proved that you cannot have all three. And this led to a big dilemma because now we have to figure out a way to interpret what quantum mechanics actually means in a way that is not locally real with measurement independence. And so here we have, Bill talked about the Copenhagen interpretation, which is also known as the shut up and calculate interpretation. And it tells you nothing. It basically says, when you're not looking at it, it's a wave. When you look at it, it suddenly becomes a particle. And then sometime later, it's a wave again. The math works. You just like do the math. Don't think about it too hard. Problem is, Copenhagen interpretation doesn't tell you what the wave function is. It doesn't tell you if it actually exists. It doesn't tell you what measurement means. It doesn't tell you how the collapse happens. It just tells you, well, this is what we observe. And so that kind of became the orthodox interpretation. And this is what you'll be taught in undergrad. This might even be what you're taught in grad school. Next up, you might have heard this one because this was really poetic. Many worlds interpretation. How many of you guys have heard like, ooh, quantum mechanics causes like a multiverse situation? Yeah, okay, some hands went up. So by the many worlds interpretation, the wave function never collapses. You just become, I'm trying to go back. You just become entangled with the quantum particle, and you are part of this ginormous universal wave function, which is weird, but which is like fine, but that means that now you're in a superposition of observing things. We go back to the cat example. I would be in a superposition of observing my cat asleep and awake. I don't know about you, but I don't know the last time I felt like I was in two states at once. I'm definitely in California, you know what I'm saying?
I mean, do you know that though?
Well,
Are you
that's a question, right? And so like, well, can we prove it? I don't know. That's a philosophy of science question. Another popular one is pilot wave theory. This states that you have a guiding wave, that's the wave function, but the wave function isn't really a real property. It doesn't actually exist. What really exists is some particle that is guided by the wave. But because these waves can interfere, the particle appears to have some interference-like properties. Another one is superdeterminism. This one was really unpopular back in the day. Now it's getting some, supporters. The idea here is that you reject measurement independence. You say the particle was always correlated all along with the measurement. And that's really bad for philosophy of science, or so people say, because that means, well, you don't have free will. That's funky. I feel like I can do whatever I want. But the benefit is you retain locality, you retain realism. So it certainly has some benefits. And then there are a few more. I can skip these because we're running out of time, but like really quickly, this one basically says collapse happens spontaneously. Problem is you don't know why that happens. Retrocausal interpretations are saying things can go backwards in time. Bill hinted at that with positrons are like electrons moving backwards in time mathematically, but we don't know how to understand it. And there's a few others we'll entirely skip those. That's a quick sneak peek of philosophy of quantum mechanics. Come find me after if you want to chat.
That's it, right?
I was gonna talk about quantum computing, but there's so much stuff about quantum computing. Look that up, he has a more
You do
unique.
1 minute?
And it's not gonna be worth it. It's more, yeah, let's.
Go watch the 3 blue 1 brown video on quantum computing.
Yeah, that was.
That's going to be another meeting.
Yeah.
What we're gonna do is we're gonna take only 1 minute, because I think what Dr. Kayla has was, but we don't have time. This is going into science fiction, basically. So they are working on that. Huh?
I think anti-gravity is squarely in the realm of science.
Yeah, so they basically, so go ahead. Tell them what it is.
I'm Christian, but most people call me Chris, so please feel free to. I started here in September of last year, and if you guys thought any of this was interesting, as I did before I came here, it would have been cool to have a club for it. So that's why I started a quantum technology club. And so we discussed different avenues in quantum, and one thing that came up was this anti-gravity thing that seemed very, very sci-fi. And so eventually we got in touch with Dr. Bill, and we started this kind of project that was purely theoretical and just like a thought experiment of looking into what could happen if we did have anti-gravity. So gravity by normal convention is a curvature of space and time. So anti-gravity would not cancel or repel this.
Okay, yeah, so, can I ask first, so who here has heard of quantum computing or read about it at all before? Okay, so I'd say over half the room, so if yeah, this is, it's just very, very basic overview of what it means. Probably won't be new to a lot of you, but if you haven't heard of it, I can just jump in here. So what quantum computing says basically, so in all of your computers, information is stored as what are called classical, so it's not quantum bits. Those are basically switches, where they're either on or off. We call it a 1 or a 0. If you ever, see in a movie, robot that talks in a big string of ones and zeros. That's what it's referring to here, these classical bits. A quantum bit, as we've now seen, in quantum mechanics, things can be stored in a superposition. So if we think back to our electron example, where it can be spin up or spin down, this is sort of like a 1 or a 0, but really, it's the information is stored as what probability do you have that when you measure your electron, you'll get spin up, versus what probability do you have that it will be spin down. And so in this way, you would think maybe you're storing a lot more information because the probability can be anything between 0 and 100%. But you're sort of limited by the fact that when you actually measure this electron, you are still only measuring either a 0 or a 1. So you can't directly measure the probability that it's in 0 or 1, but you can measure that it's either up or down. So the way that this works with quantum computing is now you get a bunch of these quantum bits together. And if you take n qubits, I should have said quantum bits are called qubits. So if you take n qubits, here we've got 3 examples here. So if we have 3 electrons, the first one can be 0 or 1, the second one can be 0 or 1, or the third one can be 0 or 1. If these were classical bits, that means that you have 8 different possibilities to store information here. But with quantum mechanics, this means that this combined system is really in a superposition of 8 different states. And so this means for any n number of qubits, they'll be in a superposition of 2 to the n states. And in some sense, and this is often how it's pitched, this means instead of doing individual calculations for each state, you can do calculations where you're kind of testing each one of these states simultaneously. This is in a superposition of all 8 of these. You run all 8 of them through some algorithm at the same time because all of it is encoded here. So you might think that this would just inherently speed up any calculations by some huge exponential factor. Unfortunately, one of the problems here is that you can only actually measure one state at a time. So if you run this through a quantum algorithm, it can in some sense test all of these at once. But when you actually make the measurement, you're only going to get one result. And so it turns out that it's kind of tricky to actually improve things using quantum computing, but there are a lot of things where it can actually make a significant difference. The most famous one being in order to factor a really large number. That's something that quantum computing can do much, much faster, like exponentially faster than a regular computer. But what I wanted to say at the end here is that it's not just a standpoint of designing better quantum algorithms to make things go faster. This is also a really exciting time on, I'm going to skip the entanglement part, but it's a really exciting time on the engineering and experimental side of things. So we've talked a lot today about all of the underlying theories and stuff about quantum mechanics. And so I just wanted to, because I was an experimentalist, throw in a little pitch for actually
Solid state experimentalist.
solid state experimentalist, which is useful for quantum computing stuff. So there's a lot of great work that's been done on what type of quantum algorithms are useful, what they can solve, but we still have to build good quantum computers. And this is a case where a lot of the most exciting technological advancements, I think, right now are happening. So even the quantum computers themselves are these exotic systems. We have cases where you trap calcium ions in like a grid of lasers and electric fields. And then each of these calcium ions, the spin up or down are your qubits. One of the more famous ones, we have superconducting qubits, where you get really small superconductors that have a magnetic field associated with the current in the superconductor, and the direction of that magnetic field is your qubit. We have new exciting ones called photonic quantum computers, where the actual information processing is done by light traveling through tiny little fiber optic cables that, like we talked about before, takes advantage of the entanglement of these different photons to actually do computation. And so there's a lot of hard problems with this, like trapped ions, for example. If you get them above like even 100 millikelvin, so like really close to absolute zero, they just like fly off into space. Superconductors also, something you have to keep really cold. This is why it's one of the biggest reasons, in my opinion, why it's so, worthwhile to be looking for a high temperature superconductor, if you've heard of that, something that would be a superconductor even near, room temperature. So yeah, this is my last little pitch here, even if you don't intend to study quantum mechanics, I think there's a lot of really difficult and challenging engineering problems that go into actually building these quantum computers. And so hopefully that's something that if it's of interest to you, you can look into more.
Like the
But
key
yeah.
takeaway is that from a theory perspective, quantum computing is kind of a solved problem. But from a materials engineering perspective, it's like really challenging.
Yeah, materials engineering, like laser engineering, like actually just like the electrical engineering of building these things and being able to read out your quantum states repeatably. Ton of really interesting engineering problems and ones where there would be a big payoff one as we make big advances here. So yeah, that was my closing.
That was awesome.
But
Oh,
can-